afternoon, everyone. It's my pleasure to welcome you to today's Brahmagupta Colloquium. We are honored to have Professor Nicolas Sisourat from Sorbonne University, Paris. Professor Nicolas Sisourat is an associate professor in Laboratory of Physical Chemistry, Matter and Radiation at Sorbonne University. Professor Nicolas received his PhD from Pierre and Marie Curie University and then did his postdoctoral research at Heidelberg University before joining to Sorbonne. His research focuses on the development of theoretical approaches and associated numerical tools for the description of ultra-fast electronic and nuclear processes. Today, Professor Nicolas will be presenting his insight in energy transfer in extreme quantum system from helium dimer to helium nanodroplet. Without any further delay, thank you, Professor Nicolas, for being with us today, and the stage is yours now.
Thanks also, Shiva, for inviting me, and Prabha for this invitation. And so good afternoon, everyone. So the title is Energy Transfer in Extreme Quantum System. So it's very ambitious. So I will narrow down to one specific energy transfer processes, the so-called ICD. I'm going to explain what is ICD. And when I talk about extreme quantum system, I'm going to focus on helium clusters. Okay. So here is the outline. So first I will explain what is ICD. So ICD stands for Interatomic Coulombic Decay, and I will explain what is it, explain what kind of processes we're looking at, its properties and characteristics. And then I prepared three examples on helium clusters. However, just don't hesitate to interrupt me during the talk if you have any question. If I'm not clear, just stop me. I would rather just present only one example, but you get something out of it, than I go through everything and you get nothing. So really don't hesitate. Okay, so let's start. So what is ICD? So I usually start to explain ICD by comparing to the Auger effect. So if you take an atom, like a neon, so you have three shells, the 1s, 2s, and 2p. And if you create a hole in this 1s orbital, so you remove one electron, then you end up with a highly excited ion that can relax. So one electron from the outer valence shell fills the hole, and this energy is used to kick another electron. So then you have a dication. So you have neon with two holes in the valence shell. Okay? Now if you try to do the same thing, but now with a hole in the 2s orbitals. So you still have an excited atom, but now this energy from this shell to this shell, it's not enough to ionize another electrons. So it means that the Auger effect is forbidden from an energy point of view. Okay? So then this ion is stuck in these states, and it can only relax by emitting a photon, which takes typically 100 picoseconds. So it's a pretty long process. Okay? What was shown in 1997 by Lawrence Sederbaum is that if you put the same excited ion with a hole in the 2s orbital, but now you put a neighbor nearby, another neon atom, for example, then you can fill the hole. So this electron 2p fills the 2s hole, and this energy is transferred to the neighbor, which is then ionized. So then you finish with two neon plus ions that repel each other. Okay? And this is possible because this state, it's much lower in energy than this one. Okay? And this ICD process was shown to be much faster than the radiative decay, much faster than by emitting a photon, by orders of magnitude. So typically ICD is within 100 femtoseconds, while, as I said, emitting a photon is more like 100 picoseconds. So since this first work, there was a lot of ICD-like processes. So we can think about resonant ICD. So now instead of ionizing an electron from the 2s, from this inner valence shell, you can just excite it to high-lying orbitals. So a bit like resonant Auger. You have other processes which was called ETMD or ETMD3. I'm not going to go into this, but I wanted to mention all those work that are related to ICD. ICD was observed in photoionization. So the first demonstration was on the neon dimer. So they took a neon dimer, and with X-ray or XUV photon, they ionized in the 2s shell, and they look at the ions and the electrons. Okay. But it was also shown that it can be triggered by ion impact, electron impact, by cascade after Auger. So you first do core ionization, then you have this Auger process, but the Auger process can leave the ion in an excited state, which can undergo ICD. So it's very general. It was observed in van der Waals cluster, but also in hydrogen bonded cluster, in quantum dots, in liquids. So it's relevant in many aspects of physics and chemistry. To understand ICD, there was a lot of work on electronic structures, scattering theory, quantum dynamics. There was also some quantum electron dynamics simulation to look at QED effect in ICD. And since the first paper, we have more than 400 papers just focusing on these ICD processes. The characteristic of ICD, as I said, it's a femtosecond time scale. It's a very fast, so very efficient processes. So in most of the case, that's the dominant process for this excited system. It was shown that the nuclear dynamics is really important because now it's in the femtosecond time scale. So it's fast, but there is still some time for the nuclei or for the atoms to move. And this has a strong impact on the process. I will show you an example on helium dimer where this nuclear motion is really important. One characteristic is that usually ICD emits a low energy electrons, so typically between 0 and 10 eV. And this is really important for radiobiology because those slow electrons are genotoxic. Usually we think that they attach to DNA and break DNA, okay, through this dissociative electron attachment. So it's really important to find all the sources of low energy electrons, okay?
That's the origin of mutation in DNA.
Yes, so we think that when you go under radiation therapy, for example, they send you like X-ray to your body. The X-ray doesn't do much actually. What it does, it creates an avalanche of slow electrons or low energy electrons, and those low energy electrons kills the tumor basically. It attaches to the DNA and kills so it's really an indirect process.
Also for mutation, they say that when ultraviolet light is absorbed by DNA.
Yeah, of course, yeah. I mean, basically, the mutation comes because you break the DNA and it doesn't repair by itself. So it's the same thing, yeah. Okay. And in the same spirit, ICD creates radical cations. I showed you that it creates ions, and those radical cations are highly reactive. So then it can just trigger a lot of chemistry and so on. Okay, so it's really important for radiation damage, but it was also shown that it can be used for chemical analysis because the efficiency of the process depends strongly on the distance between the excited atom or excited molecule and the neighbors. And so you have some mapping between the efficiency and the distance, and you can use it for analytical purposes. So for example, it was shown that if you take those hetero atomic clusters, so it's some cluster with, for example, krypton and xenon, they can be in several structures. And if you look at the ICD signature of those, they are different depending on the signature. So you can really figure out what do you have in your apparatus or in your experiment. Okay. Well, this depends. There are many experiments. So the typical signature is the ions and the electron. So if you can measure in coincidence, for example, the neon dimer, if you can measure in coincidence neon plus, and the ICD electron, then you have a clear signature of it. So that's the best case scenario. But if you have a system that is more complicated, or if you cannot measure in coincidence, there are other ways to look at it. I will show you a couple of examples for helium cluster. But let's say the typical is either the ion, the electron, and the best is to measure both of them.
How is the femtosecond scale measured? How did you figure out this femtosecond?
So how do we know it's femtosecond? So, well, we did some calculation that shows that it's within this 100 femtosecond. And there was some experiment where they look at, they did time resolved experiment. So there are two kinds of time resolved experiment. The first one is a pump probe. So you shine with some light to trigger ICD, and you come with another light to see if ICD took place or not. Okay. The other experiment was on what they call the PCI striking. So what you do is that you ionize, let's take again the neon case. So you ionize one neon atom. So you have your photoelectrons leaving, and then ICD takes place. And if the ICD electron is faster than the photoelectron, at some point it will bypass this photoelectron, and then suddenly this photoelectron will see a charge 2+ instead of a charge 1+. And so it will slow down. And so this energy shift of this photoelectron depends on the time the ICD electron is emitted. So you have a mapping between this energy shift and the time. And so like this, you can have time resolved, and they showed also that it was in the femtosecond. Okay. So that's the two kind of experiment that was done. Yeah. And this agrees well with the theory. Okay, continue. Okay, so the first example is on helium dimer. So how to trigger ICD is slightly different, but it's really the same thing, because in helium dimer you have only one shell. You have 2 electrons in the 1s orbitals, and that's it. But to create or to trigger ICD, what you can do is you can ionize and excite one helium atom. So you have one electron from the 1s that is ejected, and you have the other electron is excited to, for example, the 2p orbitals. Okay. So then you have helium plus excited, and you have enough energy here to ionize another helium atom. Okay? So at the end, you have this ICD electron and the 2 helium plus. Okay? So it's very similar than the neon case. It's just how you trigger it is a bit different. Okay? What is funny with the helium dimer is that even though it's 2 atoms, they are so weakly bonded that the nuclear wave function is very delocalized. So if here I plot the potential energy curves of the helium dimer, so that's the interaction between the 2 helium atoms, you see that you have a very small well here. It's just 1 millieV deep, but because of quantum of the the 0 point energy, the binding energy is here. It's just 100 nano EV. So it's really, really tightly, slightly bound.
So it's a bound state of 2 charged ions.
No, here it's in the ground state. So it's 2 neutral helium atoms. Yes. But because it's so light and the interaction is so weak, that they are barely bonded. Okay, it's actually only helium-4 that creates a dimer. If you take helium-3, it doesn't work. It's too light.
Mass is lower. Quantum fluctuation.
Yes, so you don't form it. Yeah.
Is the vibrational ground state?
Yes.
Okay.
There is only one, and it's spread over like 200 angstrom. So the mean distance, interatomic distance, is actually 52 angstrom. So it's a huge molecule, even though it's only 2 atoms. It's a very big molecule. Okay? And the good thing here is that we're going to probe ICD over all those distances. That's the only system that can allow us to really probe ICD over large distances. Okay? So it's the same story that I will tell, but now in terms of potential energy curves. So we start here from the ground state of helium-helium, 2 neutral atoms. Then we ionize and excite 1 helium atom, so we end up in those states. So there are 6 possible molecular states with different potential energy curves. The wave packet, which is shown in yellow, will move here, and then it will decay by ICD to helium plus. Okay? And we can measure the kinetic energy of the ions, or we can calculate it. Okay? And the sum of the kinetic energy, we call this the KER. The kinetic energy release. It's just the sum of kinetic energy. Okay? And that would be our main signature. And this is what I show here. So this is the KER. So as I said, the sum of the kinetic energy of the 2 helium plus ion. And in black, that's the theory. And in red, that's the experiment. Okay? So in the experiment, they measure the ions and the electrons. But here I show only the ions. Okay? And you see that we have a pretty good agreement. So we have a main peak here at about 8.5 eV, and this corresponds to a distance of 2 angstrom between the two helium when ICD takes place. Okay? So we have this huge molecule, we excite it, it shrinks to 2 angstrom, and then undergo ICD. And then it breaks. Okay? But if we look at the other part, I mean, at the other extreme of the spectrum, we still have something around 1 angstrom. And this corresponds to 14, we have something at 1 eV, and that corresponds to 14 angstrom. So that shows that the two helium, they can exchange this energy over such a large distances. And if you compare this to the atomic radius, it's orders of magnitude larger than the atomic radius of helium. So it's a huge distance. Okay? So it's very efficient. ICD is very efficient, even though the two atoms are far from each other. So that was the first observation for helium dimer. We can also, here it was not measured, so it's pure theory, but we can look at the partial Kerr spectra. So what I mean by partial is that I told you here you have 6 states, okay? Well, we can compute the Kerr spectrum for each of them, and they are shown here, okay? Why do I show those spectra? Is because you can see that for each of them, we have this oscillation, okay? And I want to explain what are those oscillations, okay? So I will take only one of this spectrum and try to explain it, okay? So how can we explain it? So here, it's a zoom over the potential energy curves of this helium plus excited helium, so before the decay, okay? And here, that's the final potential energy curves where we have helium plus, okay? And in black, here, that's the vibrational wave function, okay, on these potential energy curves divided by r to the 6, okay? I did divide it by r to the 6 because we know that the ICD, the probability depends on the distance like 1 over r to the 6, okay? So then you get this black, and of course you see those oscillation in the vibrational wave function. It's just the nodal structure of the wave function, okay? And now if I project this vibrational wave function, you see you have a mapping between distance, which is here, and energy, which is here, okay? And so if I do this projection, I get my Kerr spectrum. And again, I got those oscillations. So what it shows is that those oscillations, they're just a reflection of the nodal structure of the wave function, okay? So we know that it can take place at large distances, but on top of that, we can map the vibrational wave function that decays via ICD, okay? And we can go one step further, is that we can measure how those structure comes up with time, okay? How they will build with time. Sorry?
That wave function, that's the radiation.
Yes. No, of the dimer, yes. Yes, so this is what we see. Yeah. Another way to think about it is that you can imagine that your wave packet goes up, moves, and as it moves, it decays. And because it decays at different time, then you can have interference. And when it interferes, you see those structures appearing. Okay?
Consistent with Frank-Condon approximation.
Yes. It's a generalized Frank-Condon approximation. It's generalized in the way that we divide by r to the 6. While in Frank-Condon, usually you don't do that, or you use the dipole as a weighting factor. Okay.
The probability goes as r power 6, that's why you're...
Yes, so we assume that the ICD probability goes like 1 over r to the 6. Yes. Okay? Please.
Is that the effect of quantization of the potential energy?
It's pure quantum. If you do classical, you don't see those oscillations. You really need to go to quantum mechanics and really do the calculation exactly to have this oscillation. Because if you take classically, there is no nodal structure, so there is no interference, so you wouldn't see anything. I mean, I've done it actually. I've done also classical calculation, and what you see is that you get the envelope, right? So you get some kind of distribution, but you don't get the nodes. Yes.
So you'll see only the turning points.
No, you see, you imagine that you have an envelope like this. This is what you see. So you get the right distribution, but you don't get the zeros. Yeah.
These are ionized atoms, right?
At the end, they are both ionized.
So since they're vibrating, do they release some radiation?
So once you once the two atoms are ionized, they just fly from each other. They repel each other. So then there is no more vibration. The vibration is really before ICD. It's before the decay.
So that time it emits some radiation which can be probed?
You mean some infrared radiation that could be here? They don't lose energy because this would take much more time. Okay, I'll show you in the next slide how long it takes for ICD to take place, and this is much faster than emitting a photon. Okay, because to emit a photon, you need to couple to the field, to the photon field, and this is really weak. All right. Okay. So just to recap, so those structure here, you can also see it as interference at different time. Okay, so if we can do a time resolved experiment, we should see those structure appearing with time. And so we didn't do the experiment, but we did the calculation, and this is what you see. So this is again the Kerr spectrum, but now at different time after ionizing and exciting one helium atom. Okay? And at 10 femtosecond, you have this black curve here, no structure. Okay? You have something around like 3 to 6 EV, but barely any structure. Then you wait 50, 100, then you start to see things appearing. It's because your wave packet vibrate and you start to have interference between different time. Okay? And then if you go to longer time, 200, 2 picosecond, then you get your final Kerr spectrum here with all those oscillations. Okay? So you see, it's typically everything is done within, like, say, 10 picosecond, which is much faster than any infrared radiation. So we can forget about this channel.
In this case, you don't have any low energy electrons, right? There is no KER at low energy around 1 eV or 2 eV. So can you correlate, like, with respect to time, what happens to the distance between the helium atoms in the dimer?
You mean for the electron energy?
Yes.
Or the ICD? Well, you can, the ICD electron will have basically the energy between this and this. So here I have a Kerr of 8. I will have an ICD electron of 8.4 EV. Okay? And for this one, it will be much larger. So it goes to here. I will have 13 EV.
No, but in the previous one, you showed that you have this low energy electrons.
Yes.
You can correlate it, which happens at around 14 angstrom distance between the two helium atoms.
Here, that was the Kerr. It's not the it's not the electron energy. It's the energy of the ions.
Okay.
Yeah. Okay. That answers your question, right?
No, just wanted to know whether you can relate it to the electron curve.
Yeah, you will. We did that also. The electron energy distribution is just a mirror image of this one. That's all. There is nothing. There is little difference between the mirror image, but really small. So.
But with respect to time, in the electron curve, you are able to see there is no low energy electrons, right? When you show the plots where you have the electron curve for different times.
Yeah, they will be emitted at different time with some different energy. Yeah. But at the end, they will build up also, and you will have the same structure. Okay? No other question on the dimer? So maybe I'll give the last example on large. So after this initial work on helium dimer, there was some experimental work on larger helium clusters. So they took really clusters with thousands of atoms. So this is much more complicated. But they did the same. They took this huge helium cluster, or nanodroplets, then they shine lights to ionize and excite one helium atom in this. Then ICD takes place, and then many things happens. It breaks into several fragments and so on.
Is it in a superfluid state or is it high temperature?
Yes, so helium clusters are superfluid. So the temperature is 0.4 Kelvin. Yes, yeah. And it's only helium-4, I think. Yes. Yes. So they have measured, so this is what they have done on this large cluster, and they measure many things, many fragments, okay? I'm not going to talk about all of this, okay? I will just focus on this particular channel where they measure only one helium plus ion. Okay, so I just zoom over it. So they ionize and excite one helium atom, and they measure the energy of this helium plus, okay? So it's similar to the Kerr spectrum I showed you. It's just half of it because we measure the kinetic energy of only one helium plus ion. Okay? And this is for different size of the cluster. So 2 is the dimer. That's what we have seen. And it's in yellow. And again, it's exactly the Kerr spectrum I showed before, but just divided by 2.
Just out of curiosity, how do we excite just a single helium atom in such a large crystal?
Well, when you okay, the excitation can be delocalized, but this you don't control. You just shoot and wait what happens. At some point, it localized. Yeah.
Actually, at most, you could excite less than 1 or 0.
Okay, in that sense, okay, yeah. So okay, I misunderstood your question. Yeah, the intensity of the light is just enough to ionize at maximum 1. If that's your question, yes, okay. Yeah, so the yellow is the same spectrum for the dimer, okay? Just that we measure only half of the energy, okay? And if you go to 1004, then this main peak around 4.5, it decreases in intensity, and you have something appearing here at 1 eV. So that shows that after ICD, you have these 2 helium plus ions that repel each other. Well, those ions, they must lose energy because they should have 4 eV, but we measure them in large cluster at 1 eV. So they lose energy, okay? And the first interpretation by this experimentalist was that when the 2 helium plus ions fly away, they start to collide. So you have like this BL collision with the other helium atoms, and they lose energy. And this makes sense. They have some classical dynamics, molecular dynamics simulation that kind of agree with this mechanism. But a bit later, we came up with another explanation. So we did the same kind of experiment, but this time we could take helium trimer, okay? 3 atoms. So that way it's a much better way to control, and we can measure in coincidence the 2 ions and the electron, okay? So the experiment was done by the Frankfurt group using Coltrims. So Coltrims is just the apparatus to measure the 2 ions and the electron, okay? And they look at this. So this is the energy of 1 ion and the energy of the other ion, okay? And so you have this diagonal part here, which makes sense. You have the 2 helium plus ions. They repel each other, and both of them take the same energy, okay? So you have this line. But you see also here that in some cases, 1 ion is fast and the other one is slow, okay? So that shows that one of the helium ion lost energy, like they have seen in this large cluster. But here you have helium trimer. The probability that these ions collide with the 3rd helium atom is tiny, okay? And still we see it, okay? So then we did the theory. So we did the full simulation, the ICD, the fragmentation, and so on. And we have a pretty good agreement between the experiment and the theory. We see also this diagonal line, which is just the direct explosion. And we see also these slow ions, okay? And then we look at the theory to try to explain why we have this slow ion. And maybe I'll tell you first what is it, and then I'll show you why we conclude this. So what happened is that the 2 helium ions repel each other, they fly away, and you have the third helium atom, neutral atom nearby, and you can have a charge transfer between the helium plus and the neutral one. So then when you have this charge transfer, suddenly this helium plus that took this kinetic energy lose its charge, and then it's not repelled anymore. So it keeps a constant kinetic energy and flies away. And then you have this neutral helium atom that suddenly becomes ionized, and then it's repelled by this one. But now they are already far from each other. So then this one will start flying away, but with little kinetic energy. And this is what they measure. So that's why they lose energy. So it's not the billiard ball collision, it's this charge transfer that explains this.
This is 3 helium atoms.
Yes, 3 helium.
I was thinking of helium 3 lighter atoms.
Ah, no, sorry, it's a trimer. It's a trimer. So it's 3 atoms of helium. Yes, sorry. Yeah.
Here, it's not the loose, floppy diamond, right?
It's still quite loose. It's if you look at the typical distances is well, actually, you see it. It's if you do the sum of the two here, you still get 9 EV, which is no, sorry. Yeah, it's here. If you look here, you have 2 EV. It means that the distances is about about 10 angstrom. So it's still pretty large.
So there are bound atoms, the number increases. Like 4 or 5 atoms, it's even more bound.
The more you put, the more bound it is.
60 atoms, very...
Then you have a distance about 3-4 angstrom. Yes. But it's still very floppy because it's not like a structure where the atoms they just are moving all the time and so on. So it's yes. So those are really extreme quantum systems.
Loosest bound state.
Yes. Yeah.
But that's also due to the superfluid nature.
Yes. So it's everything is due to the weak interaction and the light mass, and then quantum mechanics do the rest.
Apparently, above 60, superfluidity sets in experimentally.
Mm.
I've seen signatures of superfluidity even at 60. And the number of
Okay, but I guess below you have the same mechanism, but they are so small that it doesn't make any sense to think about superfluidity. That's all. It's I guess if you have 3-4 atoms, you cannot even define really temperature, for example. So then it doesn't make any sense to talk. Yeah. Well.
fascinating that when the number of atoms is above 60, they can rotate the helium droplet and even create quantized vortices.
Yeah.
Which is normally we thought it's a property of bulk, but already at the level of 100 atoms and so on, to create quantized vortices.
Yeah, those systems are, as I wrote, extreme quantum systems. Okay. Okay, so I told you the end of the story. Maybe I'll go backward and show you how we conclude this. So here I show you the charge on the atoms, okay, for a typical trajectory. So initially you have a charge here and a charge here on those two atoms A and B, okay, after ICD, and they repel each other. So B will go that way, A will go that way, and you have the third neutral atom, which is here, okay? And when the charge, this ion passes by the C, you have this charge transfer. So you see it, here it's the charge as a function of time, okay? And initially A and B have a charge 1, and after like about 50 femtoseconds, the charge on B drops to 0, and the one on C drops to 1, okay? And if we look at the kinetic energy, this is what you see. You see that initially A and B, they gain a lot of kinetic energy, okay? And after the charge transfer, then B keep a constant kinetic energy. It's neutral, so it doesn't feel anything, right? While the other one keeps increasing, and this one gets a little of energy, okay? And this is what they measure at the end, okay? So all this missing kinetic energy is in the neutral. And so we can measure it or compute it. And indeed, here we see the energy of the neutral atom as a function of the energy of the faster ion. And all the energy that is lost is shown here. Okay? So it's a different interpretation of what they have seen in this large helium cluster. Okay. So we did some more work on the theory side. So it's difficult to really select the size of the helium cluster. For the trimer, it was possible, but we cannot just say, okay, we want 2, 3, 4. In the experiment, usually we have a large distribution, and it's difficult. But from the theory, we can say, okay, we want just a spectrum for 2, 3, and we did that up to 7. Okay, and here I showed you the number of charge transfer as a function of the size of the cluster. And what you see is that as you increase the size of the cluster, you get more and more charge transfer. So the two ions fly from each other, then they transfer energy, okay, and then you get slow ion. And if you go up to 7, you can even have several charge transfer. So this one can fly, transfer its energy, and then transfer another time, or this one transfer and this one transfer, and so on. So it gets more and more complicated, and at the end you get only low energy electrons. So, yeah. And we can, so this is the, oops, sorry. We can see it is in the kinetic energy. So if you look at the kinetic energy of the ion as a function of the size, so again at 2, we get this peak here around 9 eV, and as the size increase, you get this decrease, okay, because of the charge transfer. This one increased because of 1 charge transfer, and here it increased also because of 2 charge transfer. So if you could measure this, if we could measure this kinetic energy as a function of the size, we would see those. We could really point where we have one charge transfer or 2 charge transfer, and so on. Okay.
So these are charge transfer collisions.
Yes. So it's really it's an ion atom collision, and you have a charge exchange between an ion and the neutral atom.
And in the process is part of the kinetic energy coupling to some vibrational or like phonon type modes, but like a vibrational mode that two neutral helium may have in the droplet or oligo. Like, so losing a bit of energy successively with each.
This we didn't take into account. You could have evaporation of the helium atoms and so on. This we didn't take into account. This will also, I guess, broaden the spectrum, this kind of spectrum. But I expect that this charge transfer is much more efficient than the coupling between the electron or the motion and the phonon. So.
I was wondering whether that's the reason for that cutoff at 1. We know that the spectrum just drops.
No, I think the cutoff is just that now the distances are so large that that ICD is not likely. Okay, maybe I'll skip this part. And it's already 45 minutes, right? I need another 15 minutes. They're going to be long, so I'm not sure. Maybe I should stop here and take questions. Okay. So okay, I'll try to be brief then. Okay. So I wanted just go to the largest study that we have done on helium nanodroplets. But now it's not. It's a different kind of ICD. It's a resonant ICD. So what you do is that you don't ionize and excite a helium atom. You just excite 2 helium atoms. Okay. So you have 2 helium excited atoms, and one de-excite, and the other one is ionized. Okay. And you can do that if you put, now you need a strong, intense photon field to be able to at least have 2 excited states. Okay? Maybe I'll skip. Do I need to explain this? I don't think you need that to, yeah, okay. So this experiment was done at Fermi. It's a free electron laser, so it's very intense X-ray laser. And they use, or XUV, and they use a photon of 21.6 eV. So that's enough to excite an electron from the 1s to the 2p. Okay? And in the droplets, this excited atom relaxes quickly to 1s, 2s. Okay? And then you have 2 helium atoms in the 1s, 2s state, And as I said, one decays and one is ionized. Okay? And they wanted to do a time resolved measurement. So I think there was a question on how to measure the time. It's one way to do it. So you come with a probe, you excite your two helium atoms, okay? And you come with the pump, so you excite your two helium atoms, and later with another laser, here it's a UV probe, you probe the system. So if ICD took place, then this photon cannot do anything, okay? While if this photon comes before ICD, it can ionize the one excited helium atom and it quench ICD, okay? So by doing this at different time between the pump and the probe, you know if ICD took place or not, okay? And okay, I'll skip this part, but basically that's the result. So you see that you have something going down and up, and when it goes down, it's because of ICD. Okay. So it gives you a time here. It's maybe I shouldn't go too much into detail. So the bottom line is that we can do time resolve experiment on helium droplets. Okay. So we excite two helium atoms, one goes down, one is emitted, and we measure the time for this process, okay? And what they see is that typically the ICD takes place within less than 1 picosecond. So it's pretty fast, because if you imagine that you have a large helium cluster and you have atoms that are far from each other, because the probability to excite two atoms that are close to each other is small, right? You have more chance to have one here and one here, okay? And still we see a very fast decay, 1 picosecond. The previous work estimated that it should be 50 picoseconds, okay? So there is clearly a mismatch between this theory and the experiment. And so we try to explain how it was possible, and the explanation that we have is that once you create these two helium excited, you create like two bubbles in the droplets, okay? So here, this is the density of helium atoms. So in yellow, it's the neutral helium atoms, and in red, that's this excited helium atoms. Okay.
It's cavitation.
It creates like a bubble around the excited, because the interaction is repulsive. Yes, yes, because the potential between the helium excited and the helium is repulsive, so it creates this cavity, this bubble. Okay. But the interaction between the helium star and helium star, the two excited helium, this is attractive. So you have those two guys that are excited, they push all the other atoms away, but they attract themselves. So you see that these two bubbles, they go quickly towards each other and creates a bigger bubble, basically. And now the distance is short and ICD is fast. So it's actually what we see is really this, okay. So this is our interpretation. I will skip the details, okay, how we did this calculation and how we matched the time, but basically the take-home message is that we did time resolved measurement for this resonant ICD, and really to explain it, we show that you have this really quantum effect where you create those bubbles between the helium stars and those bubbles that just merge to form a single one and undergo ICD. Okay, and that really speed up the process. Okay. Okay, so the take-home message is, okay, ICD is a very general and efficient decay mechanism. We have done a lot of work on helium cluster, and they are really just amazing quantum system. And we, really to understand everything, we really had to go to work hand in hand between experiment and theory. So that was really important for those work. And I would like to thank my co-workers, so Len Stellerbaum, that really introduced me into this ICD business. I worked a lot with Premishil to compute this ICD width, and well, Shiva also. We have done this helium cluster and thanks for the invitation. And yeah, that's a photo of the ICD community already 10 years ago. So I think now it's even bigger. And okay, thank you for your attention. Oops.
Thank you, Professor, for such a nice presentation. We now invite questions from audience.
So I have a question. The last one, suppose you do it in helium-3 droplet. Have you tried experimentally?
I think you cannot form it. The dimer, you cannot form it. The largest, yes.
But in the cluster, is it possible to MEC comes into play?
So if you have helium-3 clusters, nanodroplets, I guess the distances would be much larger, but you would see more or less the same. Yes. But that would be a very expensive experiment, I think. I think it's more expensive, right? Yeah, I think it's pretty expensive, yeah.
It's not big, yeah, but still certainly do the, you mean the fermionic helium.
Exactly.
You would see the same thing, you think? No.
Because apparently, when you put a diatom molecule having COS inside a helium droplet, it distinguishes helium-3 and helium-4 in terms of rotation of lines beats. Helium-4, it slips nicely. Helium-3, it's always broad.
Okay. If we would look at doped helium cluster in helium-4 and helium-3, we might see a difference because now the distances and, as you said, the way things are, we would see a difference. But for just a pure helium cluster, I would expect more or less the same thing.
But even in that case, the OCS rotational spectra, which was measured by Göttingen group, they do see a solvation shell of helium even in the case of helium-4, and it rotates with the solvation shell. So there is a very proximal helium skin layer, irrespective of whether it is helium-3 or 4. So
Many years ago, saw the
Yeah. So this, for doped, we would see something, yes.
all the machines are on that model. The helium tablet sources are modeled on the Göttingen machine.
We have this excited helium, we have the attractive interaction between the two excited helium.
Yes.
And also a repulsive interaction between excited helium and the neutral
Yes.
and the ground state helium.
Yes.
What is this difference and what is the nature of this associative interaction and also the repulsive interaction?
This is quantum mechanics. It's just if you do the electronic sector calculation, you see that. So.
It's not a dipole.
No, I don't think so, because you have one excited that, okay, he has a dipole because now you have the 1s2p, but the other helium are 1s2, so, and they are weakly polarized and so on, so it's really, could probably be just some exchange term that makes it repulsive. Yes, so, yeah. I mean, this is really, maybe helium is really funny states, because if you look here, you have helium plus, and it's tiny here, but you see that actually it doesn't go like 1/r at short distances. At some point, you have a small minimum here, which is kind of weird because you have two charge. You would expect that it's just undergo Coulomb. And no, it's actually bound here. You have a quasi-bound state, and it's because of the exchange electron-electron exchange term. So I expect that it's also the same for helium star helium and helium helium. Yes.
For the helium star helium, is there a Pauli exclusion effect? That's sometimes what others say in papers.
But that's what I mean. This.
Function of the excited.
Yeah, that's what I mean by this electron-electron exchange. So the exchange comes from the Pauli exclusion. So it comes from the fact that you have to take antisymmetric wave function, and then when you do the math, you have a Coulomb term and an exchange term, and but it boils down from it comes from. Yes, yes. Probably that's what I expect. Yeah. Yeah.
Nico, maybe I'll add a question on the droplets. You had the DFT calculation for the bubble.
Yes.
And then how did you use that to calculate the ICD?
So we did not.
Okay.
So So it's really a two complementary thing. So the DFT, so it's nuclear DFT. It's not the electronic structure calculation DFT. Tells us where the distance between the two helium stars is as a function of time. Okay, but it doesn't tell us the lifetime of the ICD process, so how long the ICD process take. Okay, so for that, and this is the part that I've done, we computed what's the ICD decay width. So the width is just the inverse of the lifetime. So the smaller the width, the longer it takes for ICD to take place. Okay, and so we did it for different distances between the atoms, and we see that after 1.4 picoseconds, the two helium stars are close from each other. And at this distance, which is typically here, ICD is super fast. It's within this 100 femtosecond. So
you got the distances from the
yes,
ICD and then computed the ICD.
yes. Well, we did in parallel. So we did that to get the energy. We did that to get the width, and then we put them together to see if that explained the experiment. Yes.
What is the nature of these oscillations in the density?
This ripple, I guess it's really you have two bubbles colliding, so it creates wave. It's really like throwing two pebbles in waters, right? At some point you have those. Yes. Yeah.
So the water is quantum.
Yeah, it's
So
exactly.
the length scale, maybe to do with the rotor minimum of helium.
No, sorry, I didn't get it.
Scale.
Yeah.
Maybe it's only scale in the helium-4, the rotor minimum, the spectrum of. So I wonder whether it's anything to do with the rotor minimum length scale. Sorry, we can discuss.
Yeah, okay.
Yeah, I have one question about helium primer problem, where you see low energy, kinetic energy helium. Yeah. So shouldn't there be a cutoff in the curve for the energy of low energy helium atom that we are measuring? Because after a distance, when they are moving, the charge transfer cannot occur, right? So there will be a barrier. So in the energy curve, you will see a cutoff at a point, because now the charge transfer cannot occur.
Well, the cutoff is zero, right? It's because it's here. Basically, the minimum energy is when this ion is asymptotically far from this guy, okay? And this can take place in helium trimer because the distances are really large. If you had a more structured cluster where the distances are really defined and fixed, yes, I would agree with you. But here the distances are really large, and really the charge transfer can take place when the two ions are already pretty far from each other. You see what I mean?
Yeah, I thought there was a distance after which the charge transfer cannot occur because there will be a barrier.
There is a distance, but this distance is much smaller than the distance you can get between the ions. So that's why you don't see it. But again, if you had a more structural one, yes, you would see.
It's only valid for helium only.
Well, if you take heavier noble gas, you don't have this kind of. You have the distances are more fixed and so on. So you don't create this quantum fluid dynamics that you get in helium cluster. So,
like nanodroplet only, or the gas phase or other phase, it's also valid.
The interaction is true whatever you have in nanodroplets or in the gas phase. This interaction is pairwise interaction, so you always have it like this. Yes. So it's always repulsive between helium star and helium, and always attractive between helium star, helium stars. Yes. Okay.
We will add, if you want this and others, you have to create a piece.
In the graph that you showed where the energy is falling because of the charge transfer that you said, which is dependent on the number of atoms that you're taking. So for n is equals to 2, there's one maximum is falling. For n is equals to 3, why are we getting 2 almost equivalent peaks?
So for helium 3, you mean?
Yeah.
Yeah, you get this and this. No, wait. Yeah, this one goes down. And you mean because we have only 69 and 31, right? It's because here that's the kinetic energy of the two ions, okay? So only one lose some energy, and when you sum one fast and one low, or two fast, then you get this. That's all. So it's not the intensity of those peaks are not directly these numbers. You have to take into account that the kinetic energy of each of the fragments in this case and in this case. And when you do the proper simulation, you get this.
So, if there are no more questions, thank you, Professor, once again.
Thank you very much. Thank you.
So, Professor Bhaskara will hand over a gift to speaker.
We'll take a photograph.
Thank you very much.
Thank you.
Thank you. Thank you. Thank you.
There's helium there, you say.
There is helium.